there, folks. Today we're looking at confidence intervals on proportions. And that the first piece of that, the confidence interval, is very similar to the interval estimates that we were doing, except now we're going to have an official calculation for coming up with an interval based on our statistic that might represent the population well, okay? And then the idea of it being on a proportion just means we're dealing with data that is talking about a percentage, okay? And we'll always write it as a percent or a decimal. And it's talking about values where we are simply counting how many of this thing have happened out of the total number of possibilities, all right? It's not data where we can calculate averages and means and stuff like that. We'll have a different formula for calculating confidence intervals when we're talking about data that involves means, okay? So confidence interval, again, we're setting up an interval that represents the population proportion based on some statistical value that we found, okay? The first thing we need to do when we're calculating this is calculate the standard error, okay? And again, this is a different formula when we're doing proportions than it is for when we're doing means, all right? So the standard error formula for proportions looks like this. And essentially, this will kind of replace our standard deviation and things. This is showing us how far we have to move from that proportion in order to gather most of our data values, or in this case, in order to kind of hit on that population proportion that we're looking for, okay? In order to find that value within a certain range of values, all right? So our standard error, it's the square root of p hat. Yes, that is p hat. It just looks like a p with a hat on it. Again, very creative mathematicians naming things here. So p hat times 1 minus p hat all over n, all right? And we talk about p hat, so p hat here represents our point estimate. And again, that is the value that we are finding from our statistical measurements, all right? And then, of course, n is going to be our sample size. And that's it. You know, we find the p hat, which is our point estimate. Again, this is going to be a proportion or a percent, so we'll write this as a decimal. It's simply going to be, hey, when we actually gathered data, we found that this many out of this many people had this thing, all right? And we write that as a decimal. That is our point estimate, all right? It's the value that we found when we actually collected data, and we're using that to draw conclusions about the population, all right? So, for example, it just says find the standard error for each. It says a teacher found that out of 112 students, 90 consistently completed their homework each day. And so the point estimate for this would just be, okay, what percent did we get when we actually collected data in our sample? And so when we look at the percent of students that consistently completed their homework, it was 90 out of 112. And that is literally our point estimate. So our point estimate is the percent that we got when we actually collected data. Well, that's this. And so I plug that into a calculator. That gives me a 0.8035. And that represents 80.35%. But when we're doing calculations with percentages, we always just leave them as decimals, all right? So we're going to leave it as a decimal. We're not going to bother changing it to a percent. Understand that it represents a percent. It represents a proportion. That's why it's okay as a decimal as well, all right? So now the standard error is going to be the square root of, well, I just used this point estimate. I'm going to just round it to 2 decimal places here. So I'll do 0.08 times 1 minus 80 divided by n. And in this case, n is the sample size. It's how many people we collected data from, which is the 112. Okay. Most of the time, when for our purposes, I will typically ask you for the point estimate for that proportion to 2 decimal places, just so it represents a whole percent. All right. But I may ask you for something different than that. That's just usually what I'm going to ask. All right. And I'm just going to plug this into my calculator. Again, be really careful when you plug this into the calculator. If you have a calculator that does like math print, it makes it the easiest. But a lot of times what happens when we plug this into the calculator, you might have to plug this guy in first, hit enter, then divide by the 112, hit enter. And then if you hit the square root of the answer, there should be a button on your calculator that says ANS. that just takes the previous answer and then plugs it into the square root. So you don't have to worry about punching this all in one shot using your using all the parentheses that you would need to use, okay? And so when I plug this into the calculator, it gives me a 0.0378. All right. And usually the standard error, I'll leave to a couple extra decimal places. I'll ask you for 3 or 4 decimal places. So just make sure you're rounding it appropriately. Okay. If I look at the next one, again, it says a sample of 40 college students found that 36 regularly attend all their classes. And so again, the point estimate here is going to be the percent that I found, or the decimal that I found, from the proportion that I found from the actual data that I collected. And in this scenario, the actual data being collected is we found that 36 out of 40 students regularly attended their classes. And so my point estimate is based on that. And when I divide that, that gives me 90%, so 0.90, okay? And that's my point estimate. I now do my standard error, which again is the square root of p hat times 1 minus p hat divided by the sample size, which is the 40 students that I collected data from, okay? And again, this is a job for my calculator. I'll go a couple extra decimals when I do the standard error. That looks good, okay? So I've gone 4 decimals here. And again, just be really careful as you punch this into your calculator. It's tough to do it all in one shot with all the parentheses that you would need. It helps to kind of hit the enter button a couple times and use that answer button on the calculator, okay? This one, a sample of 50 middle schoolers found that 2 did not pass for the year. So the point estimate this time would be from the data that was collected, 2 out of 50 did not pass. And I just divide that on a calculator and it gives me a 0.04. So 4% of them did not pass. And now to calculate the standard error, it's the p hat times 1 minus the p hat, all divided by the sample size, which is the 50. Okay. And again, I plug that into a calculator. Okay, so there it is. There's standard error. Okay, and again, the standard error is going to act a little bit like standard deviation for us here, because there is no standard deviation that can be calculated when we're talking about proportions. Okay, we needed something else. This kind of fills that gap. All right. So level of confidence, the level of confidence is essentially how sure we are that the population parameter will fall within the estimate interval. All right. So when I talk about level of confidence, the confidence level is going to affect how big our interval is. But the idea is when I choose a bigger confidence level, I'll end up with a bigger interval because, again, if the interval is larger, I'm more convinced, I'm more confident that our actual population is going to fall within that range, okay? It won't be as precise, all right? So there's that, again, there's this balance between confidence and precision, all right? As the confidence level gets bigger, my range of values for the population proportion also gets bigger, okay? For that parameter, it gets bigger, all right? So that makes me more confident that the actual population parameter is within my interval, but it also makes my interval way less precise. All right, if my interval is really big, it's not going to be super precise. It'll be really accurate probably. All right, so I'm confident that it's accurate, but I won't have that precision. It won't be narrowed down that much. All right, and that's kind of the trade-off as we look at these things. As the confidence level goes up, the interval's also going to get bigger because I need a big interval in order to be confident. All right, as that interval shrinks down, it becomes more precise, but I lose that confidence level. All right. The confidence level, the way this rolls into the calculations is we'll interpret the confidence level into a critical value, all right? The critical value is simply the z-score associated with that confidence level, all right? So if I'm 95% confident, I'm going to use a z-score associated with 95% in terms of an interval, okay? Which essentially would be like the middle 95%, all right? So the middle 95% is associated with a z-score. I would use that z-score as my critical value, all right? And so for our purposes here, we're going to find the critical values for each. we're actually going to use, instead of a Z-chart, we're going to use a T-chart for this, all right? And the reason we use the T-chart is because the T-chart has a lot of standard confidence level values on it, like 95 or 99, all right? The Z-chart is a little bit more cumbersome because we have to hunt around for those values instead of just them being given to us, okay? So if I want a confidence level of 95%, I'm going to go ahead and look this guy up on my T-chart. So let me jump over to my T-chart. All right, so over here on my T-chart, the T-chart simply gives us values, and we'll use this a little bit more when we get to confidence intervals on means. That's what the T-chart is really for. But if we scroll all the way down to the bottom of this T-chart, we'll see these confidence levels listed. And so this has a bunch of standard confidence levels on it. And the rest of the values throughout this whole table simply are for calculating when we're dealing with means, all right? We don't have to worry about any of that just yet. We're only going to be concerned with this very bottom row right now, okay? And so on this T-chart, when we look at this thing, right at the very bottom of this, like we see like a confidence level right here of 80. That confidence level goes with a Z-score right here of 1.282. All right. And so this little infinity symbol, like basically this T-chart is kind of showing us a T distribution. As we get a larger and larger sample size, we should get closer and closer to a normal distribution curve. So a Z Z-scores essentially. All right. And so when we get down to infinity here, we consider these are just Z-scores written at the very bottom of this thing. Everything else on here is a T-score. And so what's nice about this thing is I just look up my standard values. The one that was in question was 95. So there's 95%. Here's the Z-score that I want. That's my critical value. All right. If I was going to do this on a Z-chart, let me jump over to the Z-chart and show you where to find this. But on the Z-chart, if I want the middle 95%, and I'll kind of use I'll use this guy right here as an example. If I had the middle 95%, that means I would have 2.5% on each side. And so I need to find the Z-score associated with 2.5%. And there's actually two of them. There's a negative version of that Z-score and then a positive version of that Z-score. So if I hunt around the body of this thing for 2.5%, I got to look all over the place until I find it. 2.5% ends up being right here. There it is. Okay. So 2.5% is right here. And notice it's associated with a Z-score of negative 1.96. Okay. In other words, the Z-scores that entrap this thing are negative 1.96 and a positive 1.96. That's my critical value. I always just use the positive version of this thing. So it's the 1.96. And really, that's the same thing that my T-chart gave me. The nice thing about the T-chart, again, I don't have to look around for it. It's always listed right there, okay? The only time we would have to use the Z-chart if we have one that's not on this list. So if I asked for 75% confidence, I would have to use the Z-chart because it doesn't exist down here on my T-chart, okay? So for 95, it's a 1.960. So let me go write that down. And we denote this as a Z with a little asterisk on it to denote my critical value. Okay, 99% confidence. Again, let me jump back over to my my T-chart. So 99% confidence right here would be associated with this guy right here. So 2.576. And that's it. We just look it up on that T distribution. That bottom row is our Z-scores, okay? So we find the confidence level we want, we look up that value. Again, the only time we'd have to use a Z-chart for this is if we had one of the values that wasn't listed at the bottom of that T-chart, okay? So now we're finally ready to calculate a confidence interval, all right? And hopefully when you look at this formula, it looks very familiar to you. It's the same thing we did when we were kind of converting from one set of data to another set of data using our standard scores, okay? We had a formula before where we take something like the mean plus the Z-score times the standard deviation. This is essentially the same formula, except now we're taking p hat. That's our middle. That's our center value that we're starting from. And we're going to add or subtract because we want to set up an interval. So we want to go both above and below that value. And now we're going to do the z-score still, which is like the standard score that we had before, except this is the critical value. So it's technically that version of the z-score. Not that that really is that important for the formula here. And then instead of times the standard deviation, it's times the standard error. Again, the standard error, like the standard deviation, is kind of giving us an idea of how far we have to move. And in this case, we have to move that far in each direction based on that z-score. Okay. And so it's just a little bit different than what we've done before, but still very, very similar. Okay. So p hat plus or minus the z-score times the standard error. For example, if I look at something like this guy, all right, I want to find this with 95% confidence. And we've already done a lot of the legwork on this. All right. This is the same example that we did earlier in the notes. Okay. And so earlier in the notes, we already calculated p hat. P hat for this one was a 0.80. Was 80%. We already calculated the standard error for this thing. All right. When we calculated the standard error earlier, it was a 0.0378. And we actually already have the confidence level, the z-score that we need. All right. This said a confidence of 95%. Well, that's one of the examples we've done so far. If we look that up on our t-chart, the z-score that we find for that one is 1.960. Okay, so we have all the pieces in place. So now it says a teacher found that out of the 112, 90 consistently did their homework. We want to estimate with 95% confidence the actual proportion of the population who consistently completes homework. So essentially, we're going to use the data that we have, that 80%, that p hat, and we're going to expand that out to say, okay, if that's the value I got, I think the actual population will be between this value and this value, okay? It's going to be between two values that are kind of centered around the data I collected, all right? So once again, my formula is p hat plus or minus the critical value times the standard error, okay? So p hat this time is the 0.08 plus or minus the z-score that we're going to use is the 1.960 times the standard error. And this is why we keep a few decimals with the standard error. We don't want it to be to get huge amounts of round off error. Okay. And so for this one, again, when you do plus or minus, it means you literally have to plug this into the calculator twice. So into my calculator, I have to plug in 0.8 plus 1.96 times the 0.0378. And when I plug in just the plus sign, it gives me this on my calculator, or rounded to that on my calculator. And now I literally plug that entire thing in again, but with just a minus sign. And when I do it with just a minus sign, or sorry, just a plus sign this time. Sorry, the first one was the minus sign. This is now the plus sign. It gives me this guy. All right. And we always want to list these from least to greatest. So I plug it in with just the minus sign. I plug it in with just the plus sign. And now I get these two values. And essentially what that is saying is we're saying now that we are 95% confident. This is how we write our conclusions. That the actual population the percentage for that will be between 0.73 and 0.87. In other words, like we found that 80% of students completed their homework each day, but we don't necessarily think the entire population will be 80%. We think the population will be somewhere between 73% and 87%. And we're 95% confident that the population will be between those two values. Okay? That's what we're calculating here. It's still an interval estimate, but it's a very precise calculated interval estimate that gives us a much more mathematical basis for why we're picking those values. Okay? And then the follow-up question here, the principal claims that 85% of students in the school complete their homework consistently. Should we support or reject that claim? And the idea is he's saying the whole population is 85%. Well, does our confidence interval justify that? And the answer is yes. When you think about it, like if our confidence interval is, we're saying the population is somewhere between 73 and 87, does he have a right to claim that the population is something like 85%? Well, absolutely, because it's within the parameters of that, it's within that confidence interval, okay? And so anything within the confidence interval is fair game to potentially be the population parameter. Okay, so yes, because it falls within the confidence interval. Okay, so 85% falls within that interval. Along those same lines, if I do a follow-up question here, it says another teacher believes that only 70% of the students in the school complete their homework consistently. Should we support or reject that claim? And from that teacher's experience, maybe they have a lower completion rate with their students, but should we support or reject 70% as the population proportion? Well, the answer is no, we shouldn't support that because once again, 70% is not within our confidence level, okay? Our confidence interval, sorry. So the confidence interval says the population is somewhere between 73 and 87%. So 70%, no, we can't support that claim because it's not justified by the values we have, okay? So no, we would reject that claim because it's not within the confidence interval, okay? That is a terrible looking because I can do better. All right. So that idea is we're trying to come up with an interval that represents where the population might actually be. All right. We use a couple things to determine that. We use a confidence level to determine how big or small this interval is going to be. And then we can kind of support or reject claims that people might make. All right. And normally this is reversed. Normally someone's going to make a claim of, hey, I think the homework completion is 70%. Then we go and collect data to see if that's true. And then we set up a confidence interval to determine if that claim holds water. All right. And so these claims would probably have been made before we collected the data, before we established the confidence interval, and then we would use that confidence interval to determine which of these we're going to support. Okay.